Electrical machinery 2. Question. Using the double revolving field theory, explain why a single phase induction motor is not self-starting. Why is single phase induction motor? A single phase induction motor consists of a single phase winding which is mounted on the stator of the motor and a cage winding placed on the rotor. A pulsating magnetic field is produced when the stator winding of the single phase induction motor is energized by a single phase supply. It consists of two main parts: a stator having one or more electromagnetic coils supplied with single phase AC power and a rotor attached to the output shaft. The rotor is made up of bars short circuited using rings at both ends, similar to a squirrel cage rotor of a three-phase induction motor. The single phase supply produces a pulsating rotating magnetic field in the stator, due to which current is induced in the rotor coils. However, due to the pulsating nature of the field, the rotor fails to produce torque for self-starting. Various techniques are therefore used to derive a quasi-rotating magnetic field for enabling self-starting capability in a single-phase induction motors. This is also known as a single-phase motor. Working principle of single-phase induction motor. The working principle of a single-phase induction motor is based on electromagnetic induction. When the stator winding is connected to a single-phase AC supply, it produces a pulsating magnetic field. The word pulsating means that the field builds up in one direction, fades to zero, and then builds up in the opposite direction. Under these conditions, the rotor of an induction motor does not rotate. Hence, a single-phase induction motor is not self-starting. It requires some special starting means if the single-phase stator winding is excited and the rotor of the motor is rotated by an auxiliary means, the starting device is removed and the motor continues to rotate in the direction in which it is started. The performance of the single-phase induction motor can be understood through two theoretical frameworks: the double revolving field theory and the cross-field theory. These theories are parallel in their explanation of how torque is produced once the rotor begins to rotate. A single-phase induction motor includes a single-phase winding on the stator and a cage winding on the rotor. When the stator winding is powered by a single-phase electrical supply, it generates a pulsating magnetic field. This term pulsating describes how the magnetic field intensifies in one direction, diminishes to zero, and then strengthens in the reverse direction. Due to this behavior, the rotor of a single-phase induction motor does not start spinning on its own. The single-phase induction motors are not self-starting and require additional starting mechanism to operate. Construction of a single-phase induction motor. The construction of a single-phase induction motor involves two main parts. 1. Stator, the stationary part that creates the magnetic field. It consists of a laminated iron core with slots that house the stator windings. 2. Rotor, the rotating part that is placed inside the stator. It is typically a squirrel cage rotor made of aluminum or copper bars short-circuited by end rings. Diagram of single-phase induction motor shown in figure. That consists of stator, salient pole, rotor, stator winding, and three-phase supply and DC supply field winding. Kindly shown in figure. Double field revolving theory or double revolving field theory. When a single-phase supply is connected to the stator winding, it produces two equal magnetic fields rotating in opposite directions with the same amplitude. The fields neutralize each other, producing a pulsating magnetic field. This pulsating field fails to produce the torque required for starting the motor. When the rotor is at rest, it experiences alternate pushing and pulling from the pulsating magnetic fields without any resultant force. As it starts rotating even slightly, it enters a zone of leading field first and then lags begin the following field. This makes the magnetic fields cut the rotor conductors sequentially, generating EMF and current in them. The interaction between the stator and rotor magnetic field produces a starting torque, enabling self-starting. Why single-phase induction motor is not self-starting? That is an important question. As discussed in double field revolving theory, the pulsating magnetic field produced by a single-phase supply fails to develop torque for self-starting of the motor. During each off cycle, the fields alternately accelerate and decelerate. The Deaccelerate the rotor alternately without providing any resultant rotational force. If the rotor is at reset, it experiences equal and opposite torque successfully without any net starting torque. Even a small residual rotating magnetic field is sufficient to get the motor into the accelerating mode. Methods like speed plate, shaded pole, and capacitor start are used to introduce a phase difference between two fields, transforming the pulsating field into a quasi-rotating one for enabling self-starting. Single phase induction motor we explain in two ways. First important way is double field revolving theory. This theory makes use of the idea that an alternating uniaxial quantity can be represented by two oppositely rotating vectors of half magnitude. Accordingly, an alternating sinusoidal flux can be represented by two revolving fluxes, each equal to of the value of the alternating flux and each rotating synchronously. Ns is equal to 120 F by P in opposite directions. The circle diagram shown in figure. Let the alternating flux have a maximum value of pi m. Its component fluxes A and B will each be equal to phi m divided by 2, revolving in anti-clockwise and clockwise directions respectively. Circle diagram of figure A, B, C, D, E is shown in notes. After some time, when A and B would have rotated through angles plus theta and minus theta, as in figure B, the resultant flux would be 2 into pi m divided by 2 sine 2 theta divided by 2 is equal to pi m sine theta. After a quarter cycle of rotation, fluxes A and B will be oppositely directed as shown in figure C, so that the resultant flux would be 0. The first waveform of double field waveform shown in figure. After half cycle, fluxes A and B will have a resultant of minus 2 into pi m divided by 2 is equal to pi minus pi m. After 3/4 of a cycle, again the resultant is 0 as shown in figure, and so on. If we plot the values of resultant flux against theta between limits theta is equal to 0 to theta 360, then a curve similar to one shown in figure is obtained. That is why an alternating flux can be looked upon as composed of two revolving fluxes, each of the value and revolving synchronously in opposite directions. It may be noted that if the slip of the rotor is S with respect to the forward rotating flux, that is one which rotates in the same direction as rotor, then its slip with respect to the backward rotating flux is 2 minus S. Each of the two component fluxes while revolving round the stator cuts the rotor, induces an EMF and thus produces its own torque. Obviously, the two torques called forward and backward torques are oppositely directed, so that the net resultant torque is equal to the difference as shown in figure. That is shown in second waveform, anti-clockwise and clockwise resultant torque. Wave shown in figure. Power delivered by rotor PS is equal to 1 minus S divided by S IS squared RA. Rotor RPM, then torque is given by TS is equal to K into IS squared RA divided by S. Total torque, and we find T is equal to TF plus TB. TF and TB are numerically equal, but being oppositely directed produces no resultant torque. That explains why there is no starting torque in a single phase motor. Slip between 0 and plus 2 is chancelled S equal to 1 and 2 minus S equal to 1. If the rotor is started somehow, say in clockwise direction, the clockwise torque starts increasing and at the same time the anti-clockwise torque starts decreasing. Hence, there is a certain amount of net torque in the clockwise direction which accelerates the motor to full speed.